Okay. Good afternoon, everyone, wherever you might be. Today, we are pleased to have a leading scientist from Kansas State University, whose field of specialty is soil science and soil chemistry. And I will leave the floor to our friend, Dr. Amarjit Basra of OCP North America, and we are pleased to have him here introduce our guest speaker. And I will come back at the end of the presentation for the Q&A session. Dr. Basra, the floor is yours to introduce our honorable speaker.
Thank you, Dr. Balif. So I'm Amarjit Basra. Good afternoon, good morning, wherever you are. I work as a chief scientist with OCP North America, which is a subsidiary of OCP Group. So although I have been in the industry for about 2 decades now, but my academics is still very dear to my heart. That's why I keep all those my academic connections alive. And thank you very much indeed to Professor Ganga HETTIARACCHI, a professor of soil and environmental science at Kansas State University. A very eminent speaker you have today. She's a leading scientist in the field of soil chemistry, as well as trace metals chemistry, the soil contaminants, what is the chemistry around that, and how to do remediation for those trace metals. But a center piece of her research group is around fertilizer reaction pathways in the soil, how to make available plant nutrients more, whether they are macronutrients, micronutrients. So that's a big one. And so the ultimate goal is to solve agricultural or environmental problems that we face in intensive agriculture. So Professor Ganga was born and raised in Colombo in Sri Lanka, actually. And she did her initial Bachelor of Science degree, honors degree from University of, I think, Paradigm there. Paradigm, okay. And it was, and she chose to specialize in agriculture at that point. A number of us would think of like medicine or engineering or pure science, but I think her father influenced her that there is a big scope for agriculture in the future, and she opted to specialize in agriculture. So after her bachelor's degree, she moved to Kansas State University, where she obtained her master's and PhD degrees. After that PhD, she, I think, worked in Sri Lanka as a faculty member for some time, and came to US to work with the Environmental Protection Agency of the United States government organization. Also worked in Australia, the University of Adelaide, which is very famous for plant nutrition research or fertilizer research. They also have a center. And Professor Ganga, it gives me pleasure to tell you that UM6V also has a center of excellence for soils and fertilizer research in Africa, which would be a very good avenue to continue the dialogue and perhaps initiate some collaborations. So I think the topic for today, altering fertilizer reaction pathways in soils to optimize nutrient use efficiency, is very topical, very important. And before we come up with solutions, we need to understand the basic chemistry around the fertilizer reaction pathways. And I think Professor Ganga is going to illustrate that knowledge using nitrogen, phosphorus, and micronutrients as an example. With that, it's my great honor to invite Professor Ganga to give her talk. Thank you.
Thank you. Thank you very much for that kind introduction. And may I share my, and it's an honor to actually thank you very much for inviting me to give this talk. Yeah, please share the screen. Yeah, so as you know that first, good afternoon and good morning. I forgot to tell that. And then I'm going to talk about altering fertilizer reaction pathways in soil to optimize nutrient use efficiency. And let me see how I can change the slides. Can I go to next slide, or do I have ability to change it?
I guess you can. I guess you can just push on the down arrow on the arrow in the computer. Yeah, just go to the arrows. Try that.
It does not work.
It does not work. Okay. Okay. Let.
So, okay, could you please reshare it again?
Share it again.
Yeah.
So stop sharing and share it again.
Yeah. Select full screen.
Yes.
Okay, let's test now.
Should I? Okay.
Yeah.
Okay. I need to do it on the screen.
Yeah.
Okay. Okay, on the screen. Okay. Hello everyone again. Just to give you a brief outline of my talk. So I will be giving a brief introduction to the topic, and then talk about whether we can alter soil nutrient cycles to enhance the fertilizer nutrient efficiency. And then I will take examples from nitrogen, phosphorus, and micronutrients when I'm talking about it. And then go to summary, and then share a little bit of concluding remarks of my talk. So the nutrients such as nitrogen and phosphorus provide vital support for human life. So as we know that application of nutrients to agriculture systems has resulted in remarkable increase in yield, facilitating population growth and improved nutritional status of people. But at the same time, overloading nutrients to soils leads to environmental concerns at various scales. So if you look at water and air pollution on local and regional scale, and climate change on the global scale. Among all anthropogenic nitrogen and phosphorus inputs, so if you look at this Shang et al. 2020, you can see that over 90% of nitrogen and phosphorus are from agriculture production. So report shows that the intensive use of nutrients has largely distorted the nutrient cycles in the Earth system. This is especially true for macronutrients such as nitrogen and phosphorus. So the example, if we look at the reactive nitrogen added by human activities in 1920, it was less than 20 teragrams of nitrogen per year. And then in 2015, it is greater than 180 teragram of nitrogen per year. So it's exceeded the biological nitrogen fixation and other type of nitrogen fixation going on around the world. So so as shown in this figure, there has been reports showing the human disturbance to nitrogen and phosphorus cycle have crossed the so-called planetary boundary of nitrogen and phosphorus, as you can see. So if you are interested in, I suggest you to go ahead and actually read this article. It's a good article. So to face this challenge, we need to combine best management practices such as precision agriculture method, different application methods, timing, and development of better or more efficient fertilizer sources. That is to ensure global food security and also to address environmental problems. Here in this presentation, as I mentioned before, so I'm going to use nitrogen, phosphorus, and micronutrient as an example to show that what are the opportunities of doing so. So the question is, can we manipulate the soil nitrogen cycle? So we can look at the input, so the nitrogen fertilizers, biological nitrogen fixation, and then the organic nitrogen, and then the organic nitrogen go through decomposition, and then the urea fertilizer or the other fertilizers added and going to end up in soil as ammonium or nitrate, depending on what type of fertilizer we added. And if it is urea or the ammonium-based fertilizers, so they go through nitrification in soil. And then nitrate is the most versatile nitrogen compound, and it is not only plant available, but also it can be lost from the system through denitrification. There can be leaching losses because nitrate retention is not that great. So when we are looking at, so in addition to that, when we add ammonium fertilizers or urea-based fertilizers, we could have ammonia volatilization, and then the biological nitrogen fixation. That's a big way of getting nitrogen, as we talked before. And then there are some minor pathways that's going to be important under certain circumstances, such as NMOX and the dissimilatory nitrogen reduction. So when we look at nitrogen cycle or any nutrient cycle, the asynchrony between the times at which the fertilizer nitrogen is chemically and positionally available in the soil with the peak of crop nitrogen demand is a key driver for poor fertilizer nitrogen use efficiency. For example, it's not synchronized well. How we can get that synchronized? So if we look at it, the literature and the research, less than 50% of the fertilizer nitrogen applied is utilized by crop in that applied year. And then in subsequent years, it could be the sum of that could be again usable if it is transformed into organic form, but the rest of it, most of the time, actually lost from the system. So the management of soil nitrogen cycle is considered as a grand challenge in this century. What are the possible solutions? So we can look at slow controlled release fertilizer formulation, as well as co-application of urea or ammonium nitrogen fertilizers with urease or nitrification inhibitors. So what is the idea of that? The slowing down urea hydrolysis, slowing down the nitrification, and then by slowing down, we are planning to get better synchrony between the nitrogen availability or the available nitrogen in soil and the plant need. And then that is going to translate into greater nitrogen plant acquisition efficiency. So here in this study is showing that the urease inhibitor and nitrogen nutrition as an example, a research study showing here the urease inhibitor used in this study is NBPT, that is the N-butyl triphosphoric trimide. And then here it shows that when it is knife in, whether we have the NBPT with UAN or not, it doesn't make difference. But whenever we surface applied UAN, where we have greater chance of losing that applied nitrogen, so that's when the urease inhibitor comes, and you can see the efficiency, or you can see the advantage of NBPT sources with that. So the urease inhibitor or nitrification inhibitors, you can see the benefit of using those wherever you see the greater losses. So here, when we are looking at nitrification inhibitors in related to nitrogen nutrition, and we can see that the nitropyrene is a most common nitrification inhibitor that has been used in the US, for example, since 1970s. And then there's a newer one a few years ago introduced, that is the portonitridine. That is also a nitrification inhibitor, and believed to be even doing better than the nitropyrene. But when we are looking at the basic of these things, like what's the mechanism, trying to understand the what it's doing, sometimes it's hard for us to say that what is it. Is it like working on ammonia oxidizers, or is it working on exactly on the nitrite oxidizes to nitrate, or the working with any type of other nitrogen transformation going in soil? So the lack of specificity is a key problem. Lack of understanding of mechanism and lack of understanding of environmental effects because of that, and how they are affecting different microbial groups. So those are the issues associated with nitrification inhibitors. So there are room for additional studies to understand these mechanisms because of it. So here another possibility to do temporary nitrogen inhibition, nitrification inhibition, or the urease inhibition using micronutrients. So before I share this or explain this research study done in mallee sandy soils in South Australia, little bit about the background. So the micronutrients, especially the things such as zinc and copper, they inhibit the enzymes and bacteria that convert urea nitrogen into ammonium and subsequently to nitrate. So we do know that we do need these as micronutrients. So on their own right, they are actually a microcrop nutrient. So when we apply them at optimal range, that the optimal rates that crop needs for their growth, so if we can enhance the nitrogen use efficiency, so we are getting two things done. So the potential for concurrent benefit of improved fertilizer nitrogen use efficiency and improved crop micronutrient status is especially exciting. So exciting discovery. So if you look at this study done in mallee sandy soil, you can see that the 20 kilogram of nitrogen per hectare as zinc urea, as you can see over here, it is as effective as 40 nitrogen urea, 40 kilogram of nitrogen per hectare added as urea to that soil. So what we think happening over here is the not only we hypothesize it, we have actually ongoing and the some studies done at laboratory scale to look at the mechanisms. So it seems like the having zinc is slowing down the urea hydrolysis as well as the subsequent transformation of hydrolyzed urea like ammonium to nitrate. So here, another possibility we can do that the co-crystallization technology. So as you know that the urea is the most used nitrogen, widely used nitrogen fertilizer. So it is very hygroscopic, meaning it is readily absorb moisture from the atmosphere, and then that lead to costly challenge regarding transportation, storage, and shelf life. And then as well as that lead to asynchrony between the availability of nitrogen and the plant needs. So that can lead to reduced nitrogen use efficiency. So to remedy these issues, slow release fertilizer technologies have been developed, but these technologies can be costly and might not have capability to release nitrogen in consistent manner. So to address this, we can actually possibly use co-crystallization technology. Here, the crystalline environment of the compound is altered without changing the molecular structure. In principle, this approach should make it possible to dial in the desirable physical and chemical properties. So the co-crystallization technology has been successfully used to develop new drugs such as anti-cancer, antifungal, antiviral, etc. With enhanced aqueous solubility. So this can be a promising technology we can use for production of desirable agrochemicals such as fertilizers. So here, this study is done by a group of chemists at chemistry department at Kansas State University, and modulating the physical properties of solid form of urea using co-crystallization technology. So as you can see that the pure urea, the concentration or the solubility of that, the 23-fold decrease in urea solubility and 66 decrease in urea solubility depending on what type of co-crystal they are looking at. So here they have urea pymalic acid as well as urea 4-nitrophenol, the two types of co-crystals of urea used for this study. So currently between Dr. Krista Crow's group in chemistry department and my group at Kansas State University, we are testing these things in lab to see how they are not only like solubility in a beaker, how they are going to behave in soil. So for this study that I'm going to share a little bit of results, we use 4 treatments, the control soil, no urea added or no nitrogen added. And then the second one is urea, pure crystal urea. And then the third one is bisurea succinic acid and the co-crystal of BUS, I'm going to call that BUS. And then the next one is the 4-nitrophenol and urea, NPU. So all treatments receive the same amount of nitrogen. So we use 14 milligram of nitrogen per petri dish and 5 replicates per treatment, 3 incubation periods and 20 dishes per time. Let me explain a little bit about how the experimental setup. So this can be used to actually do mechanistic understanding of any type of fertilizer reaction or the fertilizer source reactions in soil. So we pack pre-moist soil to achieve desired bulk density, and then added water to bring the water content to the final, whatever the water content we want to maintain. So it is, in this case, it is 50% of moisture water, maximum water holding capacity of that soil, and then incubate overnight. And then the following day, introduce treatments in the center, few millimeters below the surface. And then these dishes were closed here and then secured with a parafilm. And since it is nitrogen fertilizer, we actually place these things in a larger, these petri dishes in a larger petri dish. And then we do have a ring of a sponge saturated with the boric acid to capture ammonia. So then after that setup, we seal the lid with the parafilm. So incubated those for 2 days, 1 week, 5 weeks. So the different batches to destructively sample and look at the behavior. So at the end of those incubation experiments or the incubation period, soils were sectioned starting from the center as concentric sections. 0 to 7.5, in this case 7.5 to 13.5 and 13.5 to 25.5 and 25.5 to all the way to 43 millimeter radius. So after sectioning soils, we can measure extractable nitrogen forms, we can measure pH, we can use it to do different chemical analysis as needed. And then at the same time, recover the sponge and then extract it with KCl and then measure the captured ammonia or to determine the ammonia volatilization. So I'm going to show a little bit of results from here. So you can see that the 2 days, 1 week, and 5 weeks incubation period. And then the control is in blue and urea is in red. BUS is in green and NPU is in purple. So the x-axis is that, and then the y-axis is percent nitrogen. So it's the ammonia nitrogen volatilised as a percentage of total added. So as you can see that the 2 days we did not have any appreciable amounts of ammonia release. And then the 1 week we did detect ammonia volatilization, the measurable amounts in the urea treatment and not in the other treatments. And then at 5 weeks, we are seeing not only in the urea treatment, but little bit coming out from the BUS and the NPU, those co-crystals of urea. But you can see that the ammonia volatilization was lower in those co-crystal treatment than in the urea treatments, telling that the co-crystallization is actually the slowing down the nitrogen transformations in soil. And why is that? So if you look at that, what's going on over here, again, little bit about this graph. So you can see that the 2 days incubation period, ammonium, nitrite and the nitrate extracted from soil sections. And then the soil sections, the blue color is the first bar is 15 millimeter, 27 millimeters, so the 5187, so giving us a diameter here. So the first section, second section, third section, fourth section. So the first section is the center section. So it's going from center to the away from the center. So as you can see that here the dissolution wise, when we are looking at the 2-day incubation, the ammonium, nitrite and nitrate, we wouldn't expect nitrite that much. So the basically focusing on ammonium and nitrate, we can see that the transformation to ammonium and nitrate was slower for NPU treatment than the urea or the BUS treatment. Although we did see BUS was like effective in preventing ammonia volatilization, but when we are looking at transformation wise, it seems to be even a little bit faster than urea. However, NPU treatment seems to be the slower. And then when we are looking at the 5 weeks incubation, we can see no differences in ammonium and nitrite. However, when we are looking at nitrate, we can still see that because of that slow transformation, still nitrate is, the ammonium is transforming into nitrate, and that is reflected in the little less nitrate we can see in the NPU treatment. So we know that the nitrogen, when you look at the mechanisms, when you look at the nitrogen cycle, there are ways that we can manipulate it. We can alter that pathway. So similar way, can we manipulate fertilizer phosphorus reaction pathways in soil? So we can look at the phosphorus cycle in soil. So we have fertilizer phosphorus or animal manure, biosolids. So the organic phosphorus additions to soil. And then those are usually added to fertilizer P, specifically adding P to soil solution. And then that's where, and then if it is animal manure or biosolid, it could add part to inorganic fertilizer pools in soil solution or organic P. If it is organic P, it needs to go through mineralization to become available. And then this is where the plant available P, plant can take up ortho P, the species, this H2PO4, HPO4, for example. And then phosphorus leaching is not that critical in many soils as it does for nitrogen. So we are more concentrating on various sorption type of reactions that can happen in soil. So the sorption, so the manipulation can be done on there. So how we can interfere with, or how we can alter sorption reaction. what we call adsorption, collectively adsorption reactions. And we do know that in soils, the phosphate adsorption is mostly through chemisorption or inner sphere adsorption, very strong adsorption. And then in addition to that, we could have precipitation, that is also considered adsorption, and then the absorption. But the two main things related to phosphorus absorption would be the adsorption and the precipitation. So the manipulation can be done using fertilizer formulation. I will give you an example in a bit. So when I say fertilizer formulation, things like the ortho-P sources like monoammonium phosphate, diammonium phosphate, triple superphosphate, when it dissolves, it directly giving ortho-P phosphate P forms to soil solution, or using things like ammonium polyphosphate. And then the next option with application method, are we going to apply like broadcast versus banding, for example? So broadcast versus banding can be, depending on soil, can be effective. The one or the other. And then the other things are the manipulating sorption processes with various co-additives with these fertilizers. Let's look at that. So the possible solutions, what we have seen, liquid versus granular phosphorus fertilizer application. If we look at the liquid versus granular, what is happening, the liquid form is soluble and it could diffuse. So I will tell you how it is going to impact and what kind of soils it will be more beneficial to have it in liquid forms versus granular P. And then the other thing is using these co-additives, like such as copolymers and humic substances, such as fulvic acid with high cation exchange capacity. So they possess high affinity to polyvalent cations that could complex with or the precipitate out with added phosphorus. So when we say polyvalent cations, we are talking about aluminum, iron, and then as well as calcium. So the co-application of these compounds with fertilizers may inhibit immediate fixation and allowing phosphorus to diffuse further away from the point of application. So that can be useful in certain soils where we do have high phosphorus absorption capacity. So preventing or slowing down precipitation, favoring weak adsorption into soil. When you have co-additives, they may complex with ortho-P, and then that will favor the weak adsorption onto soil colloids and increasing the volume. So thereby increasing the, so if they are moving away from the point of application, they get more chance to diffuse through larger soil volume, and that actually dilute it, and that can minimize or reduce the precipitation. So this could lead to translating to like a greater phosphorus plant acquisition efficiency. So that's the hope, that by these kind of alterations or the manipulations. So here, this study is again an example from South Australia, where they have highly calcareous soils and trying to grow wheat on them. And then the granular monoammonium phosphate and the technical grade monoammonium phosphate, that's a liquid form of monoammonium phosphate. So the same source, but in a two different physical forms. So the picture shows that the response to fluid versus granular phosphorus at 15 kilogram of phosphorus per hectare, same soil, same phosphorus rate, but why this differential response? So this Holloway et al. Study in 2001, they have shown that about 5 to 15% increase of the yield due to like when we use liquid over granular. So let's look at what might be happening over here. So if we did the X-ray tomography to look at what is going on when we add granular versus liquid. So this is showing the two horizontal tomogram at 2 times. Here we added a granule, monoammonium phosphate to the center. And then as you can see that this is the right after adding, the tomogram, and then this is the 24 hours after adding tomogram. So the different colors is showing the density changes, because that's what captured by the tomogram. So we can get this horizontal tomogram, we can subtract from each other and can get what we call as a differential tomogram for the difference between these two. So when you are looking at it, you can see that it's not equal. So you can see that the changes, here it shows that the center actually lost the density, and then here the dark area right around the granule is showing that the right around the granule increased the density, and then the rest of the soil stays the same. So you can see that right across. If you look at the relative attenuation with the distance, you can see what I was talking about. So over here, that's the background soil density, and then in the granule, you can see the decreased density, and right around the granule, you can see the increased density. And when we compare this to the liquid, the added to the center, and then looking at like right after adding it, and then after 24 hours, we can see no difference, but at the same time, we can take the differential, like a subtract these two and get the differential tomogram, and it also shows no change as we observed in the granular fertilizer. So what is going on over here, if we think about it? So when you do have the granular fertilizers are highly hygroscopic. So they do attract moisture towards them. And this moisture in highly calcareous soils comes with calcium, so that the dissolved phosphorus trying to move out. And then against it, you have the water moving in with calcium. So that actually making phosphorus precipitating out right around the granule, so that phosphorus does not get a chance to move out. So this is explained really well by Lombi et al. Study done in 2006. So this shows the X-ray absorption near age structure spectra. So that gives us some idea about what kind of phosphorus speciation we can see in this soil. X-ray absorption near age spectroscopy is not species specific. It is like XRD. It is giving us an average picture. But still, with that average picture, we can get an idea about what are the dominant. We can look at the speciation. We can use the linear combination fitting to get the composition of the particular soil with respect to that particular nutrient species. So when we look at the phosphorus X-ray absorption spectroscopy, one thing is we can definitely look at or differentiate between iron phosphate, aluminum phosphates, and calcium phosphate. Calcium phosphate, because calcium phosphate has a distinctive secondary shoulder. So here we can see that the secondary shoulder in the monoammonium phosphate added, like the right at the center, you can see the very distinctive shoulder in there. And then when we are looking at the technical grade monoammonium phosphate, liquid monoammonium phosphate, you can see that that shoulder is not as apparent as here. So that actually explains that when you do have liquid, it doesn't really, there's no moisture attraction towards that. Instead, the liquid monoammonium phosphate trying to diffuse, and there will be precipitation, but it is not as severe as precipitation you can see with the granular P fertilizer. So selecting liquid versus granular can be effective in that case. And another example for phosphorus source and formulation matters. So these studies are done over in Kansas using not as highly calcareous as the South Australian soils that we looked at. Those soils were 70 to 90%. Some soils were like calcareous. And then these ones are going more like 7 to 10% of free calcium carbonate. So here it shows that the phosphorus source and formulation matters clearly, even in that environment. Let me show that. So when we are looking at the different phosphorus, like phosphoric acid, the monoammonium phosphate added as here 125 is actually represent the how much of the volume that monoammonium phosphate was added with. So it was total volume of 125 microliter. And then when we added the same amount of phosphorus with as ammonium polyphosphate, and comparing these shoulders, you can see that the ammonium polyphosphate is not really the calcium P precipitation after ammonium polyphosphate addition is not as intense as with other treatments. So the differences are visible when you are looking at the spectra, and then the calcium P shoulder was more visible in monoammonium phosphate added soils compared to ammonium polyphosphate added ones. So when we add ammonium polyphosphates, we can see benefits due to its slow releasing ability. So we know that the ammonium polyphosphate doesn't have all the phosphorus in O2P form. So the ammonium, the poly P need to be hydrolyzed. So that make the kind of like a slow releasing P fertilizer. In addition to that, this difference in form, like having it as ammonium polyphosphate or the poly P form, that's going to change the partitioning of that phosphorus in that calcareous soil, so that reducing the adsorption or the partitioning, and thereby keeping phosphorus soluble for little longer time. So here this review article talks about how the mechanisms of actions utilized for exploration of enhanced phosphorus fertilizer acquisition efficiency around the world. So what are the mechanisms of action when we are looking at increasing phosphorus use efficiency? So people have focused on we can put those into 4 major categories, and those are using alternative P sources, so use of P species other than orthophosphate, like I mentioned, polyphosphate versus orthophosphate. And then the slow releasers, so the reduction of phosphorus soil contact time and the surface area. And then also using blockers, so that's the disruption of precipitation reaction. So if you add these blockers with phosphorus fertilizers, and if they react with calcium, or they react with aluminum or iron, that can be like efficient blockers. And then the other thing is the inducers. Those are the stimulation of the plant microbe P acquisition. In other words, the stimulants to increase the ability of that soil to make native phosphorus more available. So you can refer to this review article about more details. In some cases, we are successful, and in some cases, we are not yet successful, but there's room for the improvements, or room for looking at different sources and different co-additives. And another recent the advancement is use of this what we call as smart fertilizers. So in this case, various the advanced polymeric materials are used as like an external coating. And then the idea is these advanced polymeric material coatings will dissolve when the temperature, pH changes. So think about that. It doesn't dissolve, but when it moves to rhizosphere, it could dissolve because of change in pH. So that's why they are called as smart fertilizers. And then they dissolve and release nitrogen, phosphorus, whatever the fertilizer we do have in the core. So that could be a exciting development if we can get that right. And then the other one is showing that similarly, we can actually have these materials and encapsulate microorganisms that can dissolve or promote dissolution of native P or native nutrients, and then introduce those to soil. And then some of these polymeric materials, especially the polymeric material used here, is not only the dissolving as it is absorbing moisture, or in this case, it is as it is absorbing moisture. So it can actually increase the water holding capacity of soil as well. So do two things in that case. So these are like the smart fertilizers, or the like a future technologies that we can explore and we can improve. And here, this example is showing the multifunctional environmental smart fertilizer based on L-aspartic acid. So here the urea co, and then they do have this the PASP based hydrogel. And then this one is going to not only increasing the water holding capacity of that soil because of that the hydrogel, and then also over time they make this urea, or whatever we have in the core, like slowly releasing it into soil. So that can be an additional advantage. So the increasing water holding capacity and slowly releasing nitrogen from urea to soil. And let's look at the micronutrients, and I am going to take zinc as an example. And then we know that the millions of hectares of arable land worldwide are deficient in plant available nutrients. So if we look at as this Alloway 2009, the map, you can see the human zinc deficiency and the soil zinc deficiency. They are like highly correlated. You can see that wherever you can see high prevalence of zinc, human zinc deficiency, we can see the zinc deficiency in soil as well. So they are correlated, telling that the soil factors can influence zinc deficiency in crops and humans. Here again, this example is from South Australia. So it's showing stubble where no zinc was applied. So that has a dirty gray appearance, and then compared to which zinc was added. And then again showing zinc deficient crops later in ripening. So the correct these zinc deficiencies, we apply micronutrients. But if you look at how we apply micronutrients, you would see that most of the time, not considering about the chemistry or how it is going to behave in soil, we apply micronutrients together with macronutrients. So the inclusion of micronutrients with macronutrients is a common practice. So let's look at what happened when we do that. So here, this is example again, the granular monoammonium phosphate. The zinc incorporated into that, and then the fluid monoammonium phosphate in a calcareous soil, monoammonium phosphate and zinc in calcareous soil. So what happened? So calcareous soils are a type of soils that you can see micronutrient deficiencies. So the high pH and then the calcareous nature, making it very prone to micronutrient deficiencies such as zinc. So when we are looking at granular zinc treated soil, this micro X-ray fluorescence map, this is mapping the zinc distribution in soil. So I am showing here zinc map, and this is after 5 weeks of addition of the granular zinc as well as fluid zinc to soil. So here, map shows that the white and the yellow, that shows the higher concentration, and when we move to blue, black shows the low concentration of zinc. So here it shows that the granular, the added zinc really did not move out. So when we look at the soil section soil and digest soils and look at it, we observe that nearly 90 to 95% of granular zinc stayed in the granule without moving out. And then when you added that with the fluid form, with the same zinc source, you would, or different zinc sources, you would see that it's actually moves freely as you would expect to see normally in soil. So what is happening over here, like I explained before, so the granules attract the moisture towards them. So in calcareous soils, those comes with calcium as well. So that trigger the precipitation of different phosphorus species, and then this precipitation of phosphorus and zinc happen right around the right in the granule. It doesn't even zinc doesn't even move out. And then in case of zinc, this is not only like after incubating in soil, soon after incorporating, like a manufacturing zinc fertilizers, you can look at it. If you added, for example, zinc was included as a zinc oxide, and if you look at what's the form of zinc in granules, you would see that if it is included into monoammonium phosphate, you would see that the majority of zinc is already transformed during manufacturing process to zinc phosphate. So that can happen even during manufacturing process, not even before introducing to soil. But once introduced to soil, it can be like staying in the granule rather than moving out. So what can we do to enhance micronutrient efficiencies? We can use chelates to enhance micronutrient delivery. What are the chelates? So those are small organic molecules that complex with micronutrients and other metal cations. So what is the advantage of it? They can alter the charge of the metal, and that can change the fate in biological and soil systems. So, for example, when chelated nutrients can have a different charge, and then the chelated micronutrient can have different adsorption capacity. So, and they could stay in solution because of that, as opposed to adsorbing into soil colloids. So there's opportunities even using chelates to do soil micronutrient mining. So here it shows that taking zinc as an example, again, the zinc and the zinc exists in soil solution normally as zinc 2 plus. When you apply zinc as a zinc soluble fertilizer, and if zinc is applied as a chelated zinc, or if you use, like, if zinc is getting chelated with the natural organic acids in soil, so the chelated zinc could have different charge. And again, even if it is a charge is not different, because it is complex, it can have a different affinity for soil particles. So if the charge is different, so there can be electrostatic repulsion. So the chelated metal remain in solution and can taken up by plants or microorganisms. So that's the way that we can use. So this example is using a biosurfactant called rhamnolipid to increase dry matter production and zinc concentration in durum and bread wheat shoots. So as summary, there are opportunities to design new or better sources of plant nutrients when we look at what's going on in soil, or when we look at those individual nutrient cycles, soil nutrient cycles, and we can see opportunities of where we can do the manipulation or the alteration. They will need to be, when we do that, we need to consider they need to be affordable to produce and transport, and be able to furnish nutrients to soil solution in a manner well synchronized with crop demand. So that's the idea. All smart fertilizers, all technologies, all the improved fertilizers, we need to have a better synchrony between the crop demand and the solution. So the thorough understanding of, as you can see, the thorough understanding of soil chemical, biological, and physical properties and processes, as well as plant processes, are tremendously useful in designing more efficient fertilizers. So as a concluding remark, I would like to show you another aspect of research going on in my group, that is actually recovery of nutrients from waste waters, different type of waste and waste waters. So here the opportunities are tremendous, and in this case, my group is collaborating with engineers. They do the technological part, they do the improvement to technological part, and then we look at the phosphorus or nitrogen, the nutrient sources, to see how they are going to behave in soil. So I think the future, when we are thinking about circular economy, we do need to think about the ways of the recovering nutrients from different waste materials. So with that, I would like to acknowledge the contributors and collaborators for the work I presented over here. The list is long. Some of my graduate students, postdoctoral fellows, and my collaborators, various collaborators from K-State and the other parts of US, as well as in other parts of the world. So with that, they open to questions.
Okay, I guess Mr. Osama must have some little problems, connection problems. Okay, well, thank you very much, Professor Ganga HETTIARACCHI, for this excellent presentation on the management of nitrogen and phosphorus, and especially the controlled release between quotation marks, and how we can benefit from the fertilizers we put in the soil. So we have about 72 viewers from all over the world who have been watching your seminar. And I'm going to go through the questions and comments and post to you some of the questions that occurred in the chat part. Okay. And the first question is from our friend Ngoni at UM6P. And he says, in the urea co-crystal research, what was in the control? Is it distilled water?
It's just water. Okay. No added fertilizer. It's just maintain at that same moisture content.
Okay, super. And there is a student from UM6P from our Fertilizer Science and Technology section, master's program. And he says, interesting topic, glad to be here. Sulaiman Basiru is a student from Nigeria, a bright student from Nigeria. Okay.
Thank you, Basiru. Nice meeting you.
Yeah. And there's another long question, and it is from Victor Gustavo. He says, Professor Ganga, what is your opinion about the use of anionic and leonardite biomineral polymers in increasing the efficiency of phosphate fertilization in highly weathered soils, as in Brazil?
Yeah, thank you for that question, actually, Victor. So it's giving me an opportunity to answer that and explain it a little more. So, what we have seen in the past, making it slow releasing, and that can be advantageous in some soils, and in some soils, especially when it comes to phosphorus. Remember that I showed example in calcareous soils. If we can enhance the diffusion, if we can get it moved to the larger volume of soil, that's advantageous over the not being able to move that well, because it's going to precipitate out. And when we look at the soils like highly weathered soils, acidic soils, like soils in Brazil, oxysoils and altisols, what we did see was, so they have very high iron and aluminum. So if we get the phosphorus to move to larger volume of soil, actually we see the opposite happening. Because then we are not exceeding the saturation capacity of that soil volume. So the absorption can be enhanced. The inner sphere absorption will make phosphorus less bioavailable. So it seems like in Brazil soils, like highly weathered acidic soils, it's better that keeping phosphorus concentrated in one place, so that it's like a banding versus broadcast. So if I am to comment on banding versus broadcast, how it is going to work theoretically, I think banding should be better, because phosphorus stayed in a small solid volume, and then it will exceed the adsorption capacity of that soil volume, and then there will be the remaining P will be available for plant to take up. And then to your answer specifically, like using this anionic and this biomineral copolymer, we did actually similar carbon copolymer carbon species, like different smaller carbon compounds, and then the larger carbon compounds like fulvic acid or humic acid. We did test that, and we didn't see, although theoretically it should work, we didn't see that that is blocking the reaction of phosphorus with the aluminum or iron and keeping phosphorus available. In some soils we did see lateral effect, but not as intense as we expect it, depending on the amount of added, the amount we observed was not that significant. So in some cases, we needed to add about 10 times the recommended rate of copolymer to see the beneficial effect. Did I answer your question?
Yeah, he cannot answer, but if he
I know.
if he's not satisfied, he will come up with another question later on.
Yeah.
But for the time being, I'm posting a question by Ali Hikmet Tataran. I guess that's a Turkish name, and we're happy of the diversity of viewers we have today. And he says, what is the best source of phosphorus in liquid form that we can apply to soil with pH 0.0 and above?
Yeah. We found that like I shared, ammonium polyphosphate, and so it's a liquid form that seems to be doing much better than the other, even monoammonium phosphate. If you add them in same form, liquid form, the diammonium phosphate or monoammonium phosphate, not polyphosphate, phosphate. So the ammonium polyphosphate seem to be superior, the dissolution wise and availability wise. So I would say ammonium polyphosphate, because you usually know we cannot access, at least for now, liquid forms of monoammonium phosphate or diammonium phosphate in the market. Those are in granular form. So the study I showed, those results from the soils in calcareous soils in Kansas, though in that we were comparing ammonium polyphosphates and different monoammonium phosphate and other phosphorus sources in liquid form. So we did see clear difference between ammonium polyphosphate behavior and the other P source behavior. So I would say that ammonium polyphosphate, in my based on our research. I would love to actually try this in field. I think the only the field experiment where we have like in a controlled way comparisons were done only in Australia. So most of the time, what people do is when they are trying to compare ammonium polyphosphate to other P sources, they have ammonium polyphosphate in liquid form, but the other P form in granular form. so that we are not exactly comparing the source difference in that way, because we have the granular versus liquid as well, in addition to chemical differences. So I think these studies need to be done comparing, like we did in the lab, where we were comparing everything in liquid form. We need to do similar field studies to see that those observations in micro scale or the laboratory scale extend into field situations.
Okay, very good. Here is another answer. Here is another question from our friend Goni. He says, have you done an economic analysis on the potential cost of smart fertilizers? How do they compare to current fertilizers? Yes.
Yeah, that's a very good question. So I do think that the economic analysis need to go hand in hand. Like I said, we cannot just come up with solutions if they are not affordable. So I agree, and I have not seen an economic analysis for that, and I haven't personally done that. But it is something that we do consider. So, for example, with the waste and wastewater, those different new innovative engineering technologies and trying to recover nutrient sources and use it in agriculture, we do have actually agricultural economists in our group doing the economic analysis. So it's a very good question. Any technology we come up with, any fertilizer source we come up with, we do need to consider the is it affordable? Is it better than the conventional fertilizers? That's a very good question.
Okay, here's another long question from Sufyan Fall. I guess is from UM6P, I suppose, but I'm not sure. He says, very good presentations, very good presentation. My question is, recycled nutrients from wastewater by microalgae, for example, can be a sustainable solution to enhance crop production and be a good alternative for chemical NPK. So what do you think, Professor Ganga?
Yeah, I do think that again, we do need to have technologies to recover enough. Definitely, I do think that the recycled nutrient from wastewater by microalgae, that again could be more economical in some cases. So than using technologies. So new engineering technologies need to be again economical, otherwise, and then the scalable. So I would think that if we can find technologies like using microalgae or other technologies to recover nutrients, those need to be economical as well as scalable, so that we can produce large amount of, or recover large amount of nutrients and then use it as an alternative to chemical fertilizers. I am entirely not sure that whether we can replace chemical fertilizers 100%, but I think we can do the substitution. For example, we can have it as a mix fertilizer with the conventional fertilizers. So the reason I'm saying that, still to date, I don't think we do have organic sources that completely can replace inorganic sources, because of the especially for annual crops, to the immediate need of crop, immediate crop need might not be met by using other sources. But this is a very good suggestion. I do think that it could be a good alternate, or a good one to substitute some of the chemical fertilizer needs.
Okay. Our bright student, Basiru Suleiman, comes back with a long comment, and he's very much interested. He would like to see your laboratory and your team collaborating with our teams here at the School of Agriculture of UM6P. And he's making a good introduction to the students. So you are fully introduced to our students. Maybe you can, we will invite you to visit us in person when the pandemic is over.
Yeah, I'm happy to visit, and I'm happy to look into any opportunities of collaboration. Yes.
Yeah, okay, great. Thank you. And I was right. Mr. Ali Hikmet was from Turkey. Shukriya, Shukriya Ustad. Yeah.
Thanks. Thanks.
And here is, here is another viewer, Abdulaziz Ghazali. He says, is phosphorus foliar fertilization an efficient way to overcome problems in high soil pH?
So we talk about the different foliar fertilizers, but the efficiency wise, I haven't seen that the foliar fertilizers being efficient. Sometimes the foliar fertilizers can be as efficient as soil applied fertilizers, but it may not be economical. I think those are the two things that we do need to work on if we want to go that route. Those sources should be economical, and then those sources should be like as effective as efficient as the some soil applied phosphorus fertilizers. But I agree, sometimes in some soils, challenging soils, the foliar fertilization could be the way to go, but I am not sure for a micronutrient such as phosphorus. It could be economical more for micronutrients.
Okay, I'm glad that Mr. Victor Gustavo from Brazil is appreciating your reply. So,
thank you.
Yeah. I will move to the next commenter, and this is a champion in Morocco. This is a senior researcher at the National Research at the National Agronomic Research Institute of Morocco, INRA, and he says many thanks for this excellent presentation. What are fertilizers stabilizers differ from slow controlled release fertilizers? That's his question. Is there a special legislation for registering smart fertilizers or other emerging fertilizers? Again, he goes on saying, microbial dynamic is critical for these types of fertilizers. How arid, dry climate affect solubility and release of nutrients in these soils? It shows that he's an expert.
Yeah. So let me answer from first question. So what are the fertilizer stabilizers differ from slow control release fertilizers? So yeah, some slow control release fertilizers, it could be kind of like using the stabilizers to get that slow control release fertilizers, but it seems like when we say slow control release fertilizers, we are mostly talking about or referring, at least at the moment, like having traditionally referring to the fertilizers having some sort of a coating that need to be dissolved for fertilizer to dissolve. So considering that as a slow control release fertilizer. But in my presentation, I even consider ammonium polyphosphate as slow control release, kind of slow release fertilizer, because ammonium polyphosphate is not directly in the form that all phosphorus is not in the form that available for plant uptake. It need to go through one conversion to be available for plant. So I consider that as slow release fertilizer too. So I think we need to define what we consider like is a stabilizer, slow control release fertilizer, what we meant by that definition. So the next question about the special legislation for registering smart fertilizers or other emerging fertilizers. So this might be something that the Amarjit might be able to answer more than me about that. Um, as far as I know, those may be going through the same kind of procedure when we are registering other fertilizers. That's what I think. But Amarjit might be a good one to answer that question. And then the microbial dynamic is critical for these type of fertilizers. I agree, especially the how dry, that is also going to be critical. So if you do have, for example, drier soil, where we tested like in calcareous soil, if the soils are dry, I would expect those differences to be even more, because the granular versus liquid in calcareous soil, the difference between those fertilizers to be even larger when we do have dry or arid climate. I agree. And then the microbial dynamics, yes, of course. So I don't know whether you are familiar with that. There's the full zinc fertilizers, inclusion of different zinc fertilizers, and then also inclusion of sulfur in monoammonium phosphate fertilizer. So inclusion of sulfur, there are products that including inclusion of this sulfur in elemental sulfur form. So the idea is the elemental sulfur oxidation to sulfate, which is a microbial process. That process generate the protons, and then these protons will help to keep the micronutrients in that fertilizer or the other nutrients in that fertilizer in more soluble form. We are completely relying on that elemental sulfur to oxidize to sulfate sulfur. But we see that when we apply these kind of products in soil, and especially the soils in like the colder climates and drier areas, we don't see that's happening. So we do not see that. It takes long time. It doesn't happen within one season, so that we do not get the benefit. Although it sounds nice in the lab and theoretically sounds good and strong, but still it's not happening. I agree. The everything need to come together for those to work. That's a very good observation.
Thank you very much for this question. Maybe this is the opportunity for me to thank my friend Dr. Mrabat for his loyalty and his regularity. He's a regular viewer of our webinars. So now you had viewers from Turkey, from Brazil, and from Nigeria. These are the ones. Francis Namdi says, thank you very much for this presentation. And now here is another, he's a student from, I guess, Morocco. She says, many thanks for this insightful presentation. I'd like to know what the most efficient applied strategy to enhance the uptake of zinc using zinc solubilizing bacteria. So a topic that is related, yes. Zinc is
I do think that the if we can remember that I showed that example, sometimes using the coding, like a coded the inocula, kind of like inoculating or introducing those to soil. That way, if soil doesn't have it already, and then the other thing would be that doing things to enhance the activity of bacteria. So we may have native bacteria in soil that capable of doing that. So I would think that any type of organic carbon source addition, like a compost manure, if we have access to, those could enhance the activities of soil, native microorganism activity. And then if we don't have that, there can be benefits of introducing the solubilizing bacteria. So this is not an area that I do have current research on. So it is something that need to be tested, and it has been done in introducing inoculums, microbial inoculums with seeds, and introducing those with fertilizers. It has been done, and some benefits have been observed.
Good. Well, our friend Guni thinks, he says, thank you so much, Professor Ganga. This was a 5-star presentation, of course. Yeah, I wanted you to know that. And thanks are emerging from other viewers, such as Dr. Abdulaziz Al-Ghazali and other viewers as well. All they thank you for this interesting presentation. And some of our viewers are correcting my statements, and that's good. I'm happy to learn that Mr. Sofiane Fall is a student in Morocco at the Masir Research Center, one excellent research, agricultural research or research organizations in Morocco that is linked to UM6P.
Thank you.
So,
thank you.
Yeah, they are all happy with your presentation. And I can go on and on. I don't think we will finish the many thanks. Let me look for the questions to post, and our digital experts will share with you all the recording so that you can go over and answer them individually. And Victor Okuku from Kenya. Nice. Thank you for joining. Daniel Allo, many thanks from Côte d'Ivoire. Okay. And let me see. This is a long text. I want to show what that is. I'm Victor Okuku from Kenya. Looking forward to be enrolled in Mohammed VI Polytechnic University. This webinar are so insightful. Thank you. Well, we thank our contributors, our eminent professors from different universities of the world, and they are rendering a big service, a great service to Mohammed VI Polytechnic University, and certainly we will look to collaborate with them closely so that we can give them the opportunity to come over here and teach in our class and our programs. Good, super. And what else? Yes. And yes, let me show this one too. Yes, Mandela Elena, thank you very much for this insightful presentation, which is more effective for zinc application, foliar or soil. And our friend Mandela is from Ghana.
Yeah.
Soil Research Institute, Ghana.
Yeah. So if you do have challenging soils like zinc deficient soils, highly calcareous soils, alkaline soils, high clay soils, sandy soils, etc., if we can afford to, foliar zinc application can be effective. Especially when we soil apply those fertilizers, if we can see fixation type of reactions. By fixation in loosely, I mean transforming into unavailable form quickly, then it might not be, although it's cheap option like soil application, it might not be effective, so that you lose money. So in those cases, foliar application can be effective. Foliar application. Again, it depends on, remember that I was showing that NBPT example, the urease inhibitor. It was more, it was beneficial when we do have that nitrogen loss problem. Whenever we don't have it, it may not be useful.
Okay, do you know this gentleman by the name of Muhammad Al-Mutari?
Yes. He is one of my former students, yes.
Yeah, he's from Saudi Arabia. Apparently, he's a student at Kansas State University.
Yes.
That's good. I think University of the World is doing a great job as peacemakers throughout the world. must encourage the collaboration between all the universities. Yeah, very good. Well, Eloine Duba from Côte d'Ivoire. He sends also his thanks, or her thanks. We cannot. I personally cannot tell. Well, we have gone 21 minutes over time, and I don't mind continuing. But I think Professor Ganga HETTIARACCHI did a good job, and we are pleased with that. I would like to thank her very much on your behalf, and hoping to see her sometime visiting Morocco, or at least establish good collaboration with UM6P in Morocco. Do not forget the virtual exchange project that I will be waiting for the address of the Dean of International Program of Kansas State U.
Yeah.
And
Yeah,
thanks to our great friend, Dr. Amarjit Basra, for having suggested the name of Dr. Ganga HETTIARACCHI for this excellent seminar. And I will leave the floor to him for the closure of this excellent session.
Thanks, Professor Ganga, for a very insightful, very exciting, interesting webinar. And you can see the participation from so many countries, and that's really encouraging. And that's the purpose of such webinars, right? So students and faculty exchange of ideas, and I would encourage that people who are interested make or have further questions, make contact with Professor Ganga. Maybe you can share the contact information, Dr. Bulif. Yes. And if some collaborations could be built, that would be a great outcome of a webinar like that. That would be very productive. Thanks again, Professor Ganga. We really appreciate your contribution.
Thank you so much for inviting me, and then also thanks everyone for listening and asking very interesting questions, engaging questions.
Thank you very much. This is before we leave, we will make some advertisement for our master's program, and I hope that Mr. Osama is not there. He's there, yes. He's we are now we are recruiting the 4th cohort of our students for the master's program in fertilizer science and technology. And this is an opportunity for us to diffuse the message to all our viewers, and we will be happy to select the best students, and they can start their application on this website, my.um6p.ma. And for more information, they can either send an email to the ESAFE at um6p.ma, or drop a message, a WhatsApp message on the number shown in the screen, or basically visit the website of ESAFE, the School of Agriculture, at UM6P, and get all the information about our master's program. And with that, I will say hasta la próxima. See you next time. Inshallah. See you next time. Okay, bye-bye, everyone.
Bye.
Okay.